So again, from last time, if we want to study a reaction and how it's proceeding, we want to know the rate law. So we want to know what the rate depends on. So we can measure the rate, but we want to know what K is, and we want to know the order of the reactants. So this was, again, our kind of general reaction. If we have speed V going to some C. So the things we want to know, again, are rate constant, and we want to know how the reaction rate depends on X and Y. So typically, you can't really directly measure X and Y, or maybe the rate constant. So what we can do experimentally is we could measure how, so this is our kinetics experiment, finally. So we can measure the concentration of A over time, either through different techniques. You can do UV-vis spectroscopy, you can do NMR spectroscopy. There's all kinds of methods to get out how this concentration is changing over time. So if A is a reactant, it's going to decrease. So usually something like that. And then so this is how we can get out our reaction rate. And then typically what you'll want to do is then vary our concentrations of A and B and see how that affects our reaction rate. And therefore we can then solve for K, X, and Y. So we'll do some examples of that, like actually a more rigorous method. But for this talk, we'll talk a little bit about the method of initial rates. So what this does is, in this starting regime here, when the reaction is first starting, if we follow this plot, this region is approximately linear. So if we want to find dA over dt, remember our reaction rate is going to be equal to -1 over A dA dt. We can just take two data points. If we just immediately take, so we know our starting concentration, which I'll put in blue. So this is our concentration at T0, so A sub 0. And then all we have to do is, if we can get it fast enough, if we can just measure one data point here, then this will be our A at whatever time T is. And then just by taking this difference, so what we're saying is that this concentration change over T, so this is delta A over delta T. So this is kind of our delta T. So whatever time point you're taking here, this is time 0, right? So here's 0, here's T. So this is going to be approximately related to dA dt, because we're saying it's in this sort of linear regime. And so from that, we can get out reaction rates. So this is our method of initial rates. It, of course, doesn't apply over here, because if we were to subtract A0 from this A data point, we would end up with some sort of line, which is not dA dt, right? dA dt is actually this slope here. So doesn't apply. Can't do this at later data points. Other restrictions are, so this is, let's see. Oh, so this is our method of initial rates. This is how we can get out to reaction rates. So the limitations of this method are we can't do this at later t, and so we lose key information about mechanism that comes at later points. Lose key info from later. So as a result, this method is not really widely used, but it might be useful for some preliminary measurements of rate law. And often I think this is also gone over in high school chemistry, but we'll just do a quick example of how to apply this for the method of initial rates. So here's the example we're going to do. Let's see. Here's my example of how we can use initial rate points to then solve for rate law. So here's our overall reaction. We are looking at the reduction of nitric oxide. This is nitric oxide with hydrogen gas. And then this gives us 1 molecule of dinitrogen, and then 2 molecules of water. So again, our rate law does not equal necessarily NO squared H2 squared, because again, this is our overall stoichiometric reaction. It doesn't tell us about the key elementary step. So instead, we have to realize that it's going to be equal to some K times NO x H2 y. So we need to solve for, again, K, X, and Y. So for the method of initial rates, what we'll do is try to measure the initial rates at different starting concentrations of nitric oxide and hydrogen. And then from that, we can then back out X, Y, and K. So here's my data table. So suppose that we did 3 runs, and we varied our initial nitric oxide concentration, our initial H2 concentration, and then again, we're measuring our initial rates. So which again is in molar per second. So here is my data table. And here are our data points. Let's say for run 1, we had 0.005 molar. This was 0.002 molar. And then we have our rate was pretty slow, 1.25 times 10 to the minus 5 molar per second. For 2, let's say this was, we doubled the concentration of nitric oxide, so 0.01 molar. This was 0.002 molar. And this was and 3, it was 0.01 molar and 0.004 molar. And this was -4. So what we can do is, let's say we take rate 2, divide by rate 1. I'll do this in green. So rate 2 over rate 1, this has got to be equal to, remember we have K, NO, X, H2, Y over K, NO, X, H2, Y. So the K's will cancel out, and then we can fill in our data. So this is going to be equal to, so for rate 2, NO was 0.01 to the X, H2 was 0.002 Y, and then this was 0.005 to the X, 0.002 to the Y. So again, our concentrations of hydrogen cancel out here. And then here, in the end, we have this equals 2 to the X equals, and then we divide the rates here. And this is going to be 5 over 1.25, which equals 4. So what we can solve for then is we know that 2 to the X equals 4, so therefore X equals 2. And then so now we have our order in nitric oxide, so we know that this is going to be equal to 2. At this point, you could then, so I'll let you do this on your own, but if you were to divide other reactions here, you should be able to also solve for Y. And then we know from solving that Y equals 1. So I'll let you do that on your own. And then from there, you can plug in your rates and your concentrations to then give you K. And then so K should be equal to, I think it was 250. And so keep in mind, this is a third order reaction. X equals 2, Y equals 1. So in order to keep our reaction rates in units of molar per second, K units have to be in m to the minus 2, s to the minus 1. OK, so overall, this is a third order reaction. So this Y equals 1. So this is third order reaction. And then so what this means is that when you think about maybe some key elementary step, we don't yet know the mechanism, but it could be that 2 molecules of nitric oxide have to collide with 1 molecule of hydrogen gas to form that key step to form this reaction of the reduction of nitrogen to nitrogen. So we'll work through a couple more examples during class and also post a couple practice problems related to the method of initial rates. But there are more advanced methods that give you far more information about mechanism and rate law that we'll talk about later on.